We're now going to begin our study of antiderivatives and the indefinite integral. Now, if you recall what we've done previously, in our study of the derivative, we started with a function f of x that we're given, and then we take the derivative of this function and we obtain a new function. Call it f prime, or df dx. And what this function measures is it measures the slope of lines tangent to the graph of the function that we were given, f of x. Now what we're going to do here is we're going to sort of go backwards. So we're going to be given a function f of x, and we want to find some function, call it capital F of x, in which when we take the derivative of capital F, we get the function that we were given. So we take the derivative of this capital F and we get what we were given. We call the function capital F then an antiderivative for the function little f. And that's our definition up here that we have. So a function capital F of x is called an antiderivative of a given function little f if the derivative of capital F equals little f, the function that you're given. So that's what an antiderivative is. It's sort of going backwards. Now, if you recall, there were lots of applications for derivatives. We thought of the derivative as a rate of change, like velocity and acceleration. Derivatives measured where a function was increasing and decreasing, and the second derivative measured where the graph was concave up and down. We had min-max problems and related rate problems. Now, as it turns out, the antiderivative also has lots of useful applications. In particular, it's related to finding the area underneath the graph of a function, and that's called the fundamental theorem of calculus. So if you're given the graph of some function and you want to find the area bounded underneath the function from, say, 2 points, let's say A to B, so you want to find this area bounded between the graph and the x-axis. As we'll see, finding that area is related to evaluating the antiderivative at the points A and B. So it's quite an amazing result, and that's called the fundamental theorem of calculus. And there's lots of applications why we would want to do this. One application is that it's related to finding the work or energy imparted to an object as a force is applied to it. So that's a physics application. Finding antiderivatives will also be necessary to derive equations of motion, like the equation of motion for an object thrown upward or downward near the surface of the Earth that we've been using. So we can derive this equation using antiderivatives, and we'll do that later on. Now take note of one other thing here. Finding antiderivatives is not nearly as easy as taking derivatives of functions. So, if I were to give you a sort of a complicated function like this, say the square root of the sine of x squared plus 3x plus 1, it's actually fairly easy to take the derivative of this function. You would just have to use the chain rule. But to find an antiderivative of the function like this would be very difficult. And in fact, if you take calculus courses after this one, like Calculus 2, you'll devote a lot of time to looking at and developing techniques for finding antiderivatives for some common functions. So it's not nearly as easy as taking derivatives. Now let's start out with a few examples here to illustrate antiderivatives, finding antiderivatives in particular. So here, let's note that if we're given the function x squared, suppose we're given f of x little f equals x squared, well, notice that capital F equals 1/3 x cubed is an antiderivative for this function. Because if we were to differentiate this, you drop the 3 down, cancels with the 1/3, subtract 1 from the exponent, and of course you get x squared. So this is an antiderivative for x squared. However, it's not the only antiderivative, since notice that if we were to differentiate 1/3 x cubed plus 5, you also get back x squared for the derivative of this function, because if you differentiate, of course when you differentiate this, the derivative of the constant goes to 0. So this part right here is just 0, and you get back x squared. So in fact, this is one antiderivative for x squared, and this is another antiderivative for x squared. And in fact, any function like this, any function of this form, 1/3 x cubed plus any constant, is an antiderivative for x squared. Now the question is, are these all of the antiderivatives for x squared? When we write this and realize that c can be any constant, have we captured all the possible antiderivatives for x squared? Well, the answer is yes, and that's what the next theorem states. So here we have a theorem, and it makes the statement that if capital F is an antiderivative for the function little f on some interval I, then every other antiderivative, call it capital G of little f, must be of the form capital F of x plus c, where c is some arbitrary constant. So in other words, once you find one antiderivative for a function little f, then every other antiderivative g is going to be of the form f of x plus c. So for example, we note that 1/3 x cubed is an antiderivative for x squared, because when we differentiate this we get back x squared. So every other antiderivative for x squared is of the form 1/3 x cubed plus c. So knowing that 1/3 x cubed is an antiderivative for x squared, we have then captured all possible antiderivatives for x squared. Now let's take a look at this. Oh, and by the way, we're not going to prove this theorem right now. We'll save that for a later video, or you can certainly read it in any calculus text. Now, given that theorem, here is our definition for what we call the indefinite integral. So if we're given an antiderivative, capital F, for some function little f, on an interval I, then this notation right here looks a little funny. You may have never seen this before. This little symbol is called our integral symbol. So we read this as the antiderivative of little f with respect to the variable x, and we call that our indefinite integral. This represents the family of all antiderivatives for little f over some interval I. And by the previous theorem, the family of all antiderivatives of little f will equal capital F plus some arbitrary constant. So if you know one antiderivative for little f, all of the other antiderivatives are going to be of the form capital F plus c. So this simply represents, this notation right here, simply represents all the antiderivatives for little f. Now, just a note down here, for the indefinite integral, we call the function f of x the integrand, and the dx term is used to denote the variable of integration. And as we'll see later on when we look at the fundamental theorem of calculus, there's a good reason for using this dx term, because it's going to be related to a small finite change in x, delta x. Now let's consider this. Let's take a look at a few examples here. where we evaluate indefinite integrals. So if you'd like to pause the video here and do a few of these on your own, you certainly can. Let's evaluate the indefinite integral for the cosine function. Well, we have to recall that the derivative of sine equals the cosine of x, right? So then, what we have here now is that the sine x is then playing the role of our capital F from our previous discussion, and the cosine x, that's our little f. So the indefinite integral of the cosine of x is then going to be just the sine of x, that's our capital F, plus c. And that's all we have to do. We just had to recognize that the derivative of sine is cosine, so the sine is our capital F, and then we just add on our arbitrary constant. What's the indefinite integral of the sine function? Well, just note that d dx of negative cosine x. Now we can move this negative outside like that when we take the derivative, and so we get here. And remember, derivative of cosine is negative sine, and then two negatives make a positive, so this is just going to be sine x. And so what we have here then is that the negative cosine is then playing the role of our capital F, so that's our capital F. And the sine x was the little f that we were given. And so we see then that the indefinite integral of the sine of x is going to be negative cosine x plus c. Let's take a look at this one. We want to find the indefinite integral of x to the fifth power. Well, let's note that if we differentiate x to the sixth, we get 6x to the fifth. Now this is almost what we want. We want to get back x to the fifth power, but we don't want this 6 right here in front. So what are we going to have to, how can we modify this x to the sixth so that when we differentiate it, this 6 doesn't appear here? Well, what we can do is just multiply this by 1/6. So if we look at the derivative of 1/6 x to the sixth power, notice that this is a constant, so we can just move it outside. And now when we differentiate this, we get back. And of course the 1/6 and 6 cancel, and we get x to the fifth. And so now we have found an antiderivative for x to the fifth. So this is one antiderivative for x to the fifth. So that means that this indefinite integral of x to the fifth is going to be, and there we go. So this represents once again the family of all antiderivatives for x to the fifth. Now we will see that we have rules for evaluating antiderivatives for some pretty simple functions, and we'll get to that in a second. Now let's take a look at some properties of the indefinite integral that will help us to evaluate antiderivatives of functions. So to start, we're going to assume that c and k are some arbitrary constants, and that the derivative of capital F is little f, and the derivative of capital G is little g. So we're given these functions. Now, in this column here, in the first column here, we have differentiation rules that we're familiar with. And then in the second column, we have the corresponding anti-differentiation rules that result from the rules in the first column. So let's take a look at these. Now let's note that if you take the derivative of any constant, you get back 0. Right? Remember that rule? And so what we have then is the indefinite integral of the 0 function is just any arbitrary constant function. And that's because if we take the derivative of this, we get back 0 if we take the derivative. Similarly, the derivative of k times x, where k is some constant, is just k. Remember, you can move this k out in front of the derivative, and then you get k times the derivative of x, which is just 1. So you get k. So because of that, we then have that the indefinite integral of k, the indefinite integral of k, is k times x plus c. Because if you differentiate this, you recover k. And that's because of this rule right here. Since the derivative of k times capital F is k times the derivative of capital F, in other words, you can move the k out in front of the derivative, you can do the same thing with the indefinite integral. You can move the k out in front of your integral symbol, so you get the indefinite integral of k times f is k times the indefinite integral of f, and that's called our constant multiple rule. So what you can think of this as being is you can think of this as being your capital F plus c, and so if you multiply this by k, you get, so this is what's going on here, and if you distribute the k, you get k times f plus k times c, but k times c is just another arbitrary constant, so we can write that as k times f plus some other constant, and we'll just call it c once again. And notice that if you differentiate this, because of this rule, rule number 3 over here, when you differentiate this, you will get back k times little f. Remember this rule, this is our sum and difference rule for differentiation. The derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. So in other words, you can distribute the d dx to the f and the g individually when they're being added. Because of that, we can do the same thing with the integral symbol. The indefinite integral of f plus or minus g is the indefinite integral of f plus or minus the indefinite integral of g. And what you can think of here is think of this as being your capital F plus some arbitrary constant, we'll call it c1, and think of this as being your function capital G plus another arbitrary constant, we'll call it c2, and when you add or subtract them, let's say we add them, you get capital F plus capital G plus, and when you add c1 and c2, you just get another arbitrary constant c. And notice, if we differentiate this, because of the sum and difference rule for derivatives, when we differentiate this, we get back f plus or minus g when we differentiate. Now here's an important rule. This is called our power rule for antiderivatives. Notice that the derivative of 1 over n plus 1 times x to the n plus 1 is x to the nth power, right? If you differentiate this function right here, remember you drop the n plus 1 down, so you'd get 1 over n plus 1 times n plus 1 times x, and then you would subtract 1 from the exponent up here, so you would just get x to the nth power. And of course these cancel, and you get back x to the n. So because of this rule, we then have that the indefinite integral of x to the nth power is 1 over n plus 1 times x to the n plus 1 power plus c. Notice if you were to differentiate this, you would get back x to the n if you were to differentiate. Now the only problem here is when n is equal to -1, because obviously if we put -1 in here, if we put -1 right in here for n, we get 1 over 0, Well, obviously you can't divide by 0, so this rule breaks down when n is negative 1. So in other words, we really don't have a nice rule for what is the antiderivative of x to the negative 1, which is 1 over x. So we don't have a nice rule for what the antiderivative of x to the negative 1 is. Well, we do have a workaround for that. We can evaluate the antiderivative of 1 over x, but we need to use what's called the second fundamental theorem of calculus, and it will involve what's called the natural logarithm function. You may have seen this before. It's called the ln of the absolute value of x plus c. That's what this quantity would equal, but we'll study that in another course. We're not going to go over that right now. So just realize that the power rule breaks down when n is negative 1. We also have anti-differentiation rules for trig functions, for a few trig functions. Recall that the derivative of negative cosine is positive sine. That's because you can move the negative here out in front, and then the derivative of cosine is negative sine. So the left-hand side here is really negative of negative sine of x, and that gives you back positive sine of x. So because of this, because the derivative of negative cosine is positive sine, we get that the indefinite integral of sine is negative cosine x plus c. Notice the derivative of this, if you were to differentiate it, you would get back positive sine. Similarly, the derivative of sine is cosine, so the indefinite integral of the cosine function is sine of x plus c, because if you differentiate this, you get back cosine if you were to differentiate. And then we also have the indefinite integral of secant squared is tangent x plus c, and that's because if you differentiate tangent, you get secant squared, right, by this rule right here. Remember, derivative of tangent is secant squared. The indefinite integral of secant times tangent is secant x plus c, because the derivative of secant is secant times tangent. So when you differentiate this, you get secant times tangent. And the indefinite integral of cosecant squared is negative cotangent x plus c, and that's because the derivative of negative cotangent is cosecant squared. So when you differentiate this, you get cosecant squared. And finally, the indefinite integral of cosecant times cotangent is negative cosecant x plus c, and that's because the derivative of negative cosecant is cosecant times cotangent. So when you differentiate this, you get your integrand, cosecant times cotangent. So these are some rules that we can follow to help us evaluate antiderivatives of functions. Now let's take note of something important here. This is a very common mistake that people make. There is no common rule for evaluating the indefinite integral of the product of two functions. People make the very common mistake of trying to write this as the antiderivative of f times the antiderivative of g, and this is not true. You cannot evaluate this by trying to find the antiderivative of f and multiplying it by the antiderivative of g. And that's because if you differentiate f times g, it is not equal to the derivative of f times the derivative of g. You have to use the product rule, right? The derivative of f times g is f times g prime plus f prime times g. So because of the product rule, you can't say that the antiderivative of f times g is the antiderivative of f times the antiderivative of g. That is not true. So don't make that mistake. For example, here's a very common mistake people might make. The indefinite integral of x times cosine is not 1/2 x squared, which is the antiderivative of x, times sine x, which is the antiderivative of cosine. This is not true. The antiderivative of this is not this function here. And that's because the derivative of 1/2 x squared times sine does not equal x times cosine x. You have to use the product rule when you differentiate this, and when you do that, you will not get back x times cosine. So don't make that mistake. We do have a technique to evaluate this, by the way, but it involves what's called integration by parts, and that's for later study. Similarly, you also cannot evaluate the antiderivative of the quotient of two functions by trying to take the antiderivative of the numerator divide by the antiderivative of the denominator. That does not work either. And that also is because the derivative of f divided by g is not the derivative of f divided by the derivative of g. That is not true. And you have to use the quotient rule, right? So for example, the indefinite integral of cosine divided by x is not sine divided by 1/2 x squared. If you were to differentiate this function, you would not get back cosine over cosine of x divided by x. You have to use the quotient rule when you differentiate this, and you will not get back cosine x divided by x. So don't make that mistake either. Let's take a look at some examples now. So here we want to evaluate the indefinite integral of this function, 5x cubed plus x squared plus sine x plus 3. All right, so by the sum and difference rule, we can write that as follows. Now I'm going to write this out in detail, showing you how we use all of our rules. And once you get good enough at this, you don't have to write all this out in detail like I'm doing here. Now for the first term right here, that 5 can be moved outside, and we get now we just have to evaluate each of these. Now by the power rule, we just have to add 1 to the exponent here and here. This is going to be negative cosine x. This term right here, that's going to be negative cosine x. And this term is going to be 3 times x. And what we get then is, now when we add 1 to this exponent, we have to remember to multiply by 1 divided by 3 plus 1. So that's going to be 1/4 x to the 4th power. Notice you can think of this 1/4 as canceling that 4. If we were to differentiate x to the 4th, the 4 would drop down and the 1/4 would cancel it, so it disappears. See, we don't have a 4 in here. So we don't, when we differentiate this, we don't want a 4 up here, so the 1/4 will cancel that. And then antiderivative of x squared is going to be 1/3 x cubed. And then we have our negative cosine. And then 3x. And then always remember to add on your arbitrary constant. And there is your answer. And of course you can write this as 5/4 if you'd like. Clean that up a little bit. And there's your answer. Now notice, once you get good enough at this, you don't have to write all that out in detail. You can just simply evaluate this by thinking of evaluating the antiderivative of 5x cubed first. Now the 5 is just a constant that hangs around, so you just have to write that as 5 times the antiderivative of x cubed is 1/4 x to the 4th, and then plus the antiderivative of x squared is going to be 1/3 x cubed. The antiderivative of sine is negative cosine. and then the antiderivative of 3 is just 3x, and then your arbitrary constant. So that's how you can do this pretty quickly. You don't have to write all this out in detail like I did here. I'm just showing you how we used the sum and difference rules and the constant multiple rule. Let's take a look at another example. Let's take a look at this one. What's the antiderivative of 1 over x squared? Well, we have to write this so that we can use the power rule. Well, let's notice that 1 over x squared is the same as x to the negative 2 power. Now we can just use the power rule on this. So we can write this then as, so you see, using the power rule, the 2 right here is playing the role of the n in the power rule. That's playing the role of the n. So right here is 1 over n plus 1 times x to the negative 2 plus 1 plus c, and then we can clean that up a little bit and just write that as and we can further clean that up as and that's our answer. And just note, you could even write that as just realizing that x to the negative 1 is 1 over x. So there you go. We had to rewrite 1 over x squared so that we could apply the power rule. That's a very common technique. Here's another one where we have to try to rewrite our integrand so that we can use the power rule. So what we're going to do is we're going to split this fraction apart and write it like this. Now we can rewrite each of these fractions as x to a power, and then we can use the power rule for antiderivatives. So this is the same as, let's see, this is going to be x to the 1 minus 1/2. So this is just the square root of x, or x to the 1/2. And this is x to the negative 1/2. Now, the antiderivative of x to the 1/2. Okay, well, let's see. That's going to be, if I add 1 to the exponent, remember when we antidifferentiate, we add 1 to the exponent. When we differentiate, we subtract 1. So here we want to add 1 to that exponent, so we're going to get 3/2. 1/2 plus 1 is 3/2. Now, I want to multiply this by something so that, you know, if we differentiated this, take note of this, if we were to differentiate this, we would drop the 3/2 down and we would get 3/2 x to the 1/2. Now we don't have a 3/2 out here, so we have to multiply this by something so that when we drop the 3/2 down, it cancels. So we're going to multiply by 2/3. So there, the derivative of this function will be x to the 1/2 power. That's the same as just following the rule. You know, we could have just followed the rule 1 over n plus 1. In this case, my n is 1/2, so that's 1 over 1/2 plus 1, which is 1 over 3/2. And notice that this is just 2/3. So that's where the 2/3 comes from. We are still following the 1 over n plus 1 rule. Now let's finish off the other term. Now plus, now what's an antiderivative for x to the negative 1/2? Well, if we add 1 to this exponent here, just like we did over here, we're going to get x to the positive 1/2 power. Now note, if we were to differentiate this, we would get x to the negative 1/2, which is what we want, but we would pick up a 1/2 constant being multiplied in front. we don't want a 1, we don't have a 1/2 up here, so we want to counteract that 1/2 by multiplying by 2. Notice if we differentiate this, the 1/2 drops down, cancels with that 2, and we get the 1 up here that we want. So there's our antiderivatives, and then we just need to add on our arbitrary constant c, and there is our answer. So that's how we handle something like this. You just have to try to rewrite it so you can use the power rule. Now here's an interesting problem. We want to find a function y of x which is a solution to this problem. The derivative of y has to equal 3x squared plus 1, and y of 1 must equal 6. Now let's think about this a little bit, what we have to do. So we want to find a function y in which d dx of y equals 3x squared plus 1. Now if you think back to what we've just done, this y right here, that's basically playing the role of our capital F. And the 3x squared plus 1, that's like our little f. And so we have to find a capital F in which the derivative of that function is little f. So basically the y is going to be an antiderivative of 3x squared plus 1. So we have to find the antiderivative of this function, and that's going to be what our y is. And then we'll have to bring this into play. We'll see that this will solve for the arbitrary constant. So let's do that. So if we evaluate the antiderivative of 3x squared plus 1, notice that that is going to equal 3 times, okay, what is the antiderivative of x squared? Well, let's write it out like this first before we do that. We'll write it out like this using the rules. And now this is 3 times, alright, so what we have to do then, anti-differentiate x squared, so we add 1 to the exponent. So that's going to be x cubed, and then we multiply by 1/3. So here's 1 over n plus 1, x to the n plus 1 power, plus, and then the antiderivative of 1 is 1 times x, or just x. And then we have our arbitrary constant c. And this simplifies out to 3 and 1/3 cancel. And there we go. Now that's what our y is equal to. So y of x equals this. Notice that if we differentiate this, we get back 3x squared plus 1. The derivative of x cubed is 3x squared, derivative of x is 1, and derivative of c is 0. Now what we have to do is find a particular constant c so that y of 1 is equal to 6. So what we do now is we realize that, okay, if we put 1 in for x, we should get back 6 for y. So that means that 6 should equal 1 cubed plus 1 plus c. And so this is 2 plus c. And so therefore c equals 4. So now we've obtained a specific solution y to this problem, and it is and that's our answer. Notice, if we differentiate this function, the derivative of x cubed, 3x squared, derivative of x is 1, derivative of 4 is 0, so y does satisfy this equation. Its derivative is 3x squared plus 1, and if we put 1 in for x, we get 1 plus 1 plus 4. We do get back 6. So there is our solution. So we just had to anti-differentiate 3x squared plus 1 and use this condition to solve for the arbitrary constant. Now let's take a look at graphically what's going on here. Now graphically, this blue curve, that represents a function like y equals x cubed plus x plus some constant c. And this point right here, that's the point 1, 6. So notice that all of these functions here are antiderivatives for 3x squared plus 1. And if we notice that if we let this constant vary, we'll see that these curves move up and down, and we want to pick the one particular curve that passes through the point 1, 6. And so all of these functions are antiderivatives, and we want that one right there. And notice that when we pick the one that goes right through that black dot, that's the one where c is equal to 4. Move that up a little bit more, we see that the c is 4. And that's the one solution that passes through the point 1, 6. So that's graphically what's going on with this problem. Now let's also note something else about this problem. We have a special name for this problem. The problem y prime equals 3x squared plus 1 is called a differential equation. And y of 1 equals 6, that's called an initial condition. And we call the entire problem y prime equals 3x squared plus 1 such that y of 1 equals 6. We call that an initial value problem. And if you were to take a course in differential equations, you would study these problems in much more detail. So you can devote an entire course, well, you can actually devote much more than just a single course to the study of differential equations. And that concludes our introduction to antiderivatives and the indefinite integral.